lecture, I will explore some topics like transaction processing concepts in Unit 4 of the DBMS, and I will discuss how transactions work, why they are important, and how DBMS ensures consistency, concurrency, and recovery in multi-user environments. The first topic is transaction system. Transaction system. Let's begin with the meaning of the transaction system. A transaction system manages the execution of multiple transactions in a database and ensures integrity, consistency, and reliability. A transaction is a sequence of operations that function as a single logical unit of work. For example, when we withdraw 500 rupees from account A and deposit 500 rupees into account B, either both operations must happen together and not at all. This all or nothing nature is what ensures correctness. Now the asset properties. Asset properties to guarantee reliable outcomes, a transaction must satisfy the asset properties: atomicity, consistency, isolation, and durability. And these properties prevent data corruption and maintain correctness under concurrent access. Next is transaction life cycle. A transaction passes through multiple states: active, where operations are executing, and partial, committed, where all operations are done and it is waiting for commit, and committed, where updates become permanent, fail due to errors or system issues. Aborted, in this roll back to a previous safest days. And understanding this life cycle is important for recovery and concurrency control. Next is serializability. Serializability ensures that even if transactions run concurrently, the final outcome remains the same as if they are executed serially. This prevents anomalies and preserves consistency. There are two major types: conflict and view. Testing serializability. Testing serializability, DBMS uses two approaches: conflict serializability, where a precedence graph is constructed, and if the graph has no cycle, the schedule is serializable. And second is view serializability, which checks view equivalence based on initial read, read from, and final write. A schedule is defines the order in which operations of different transactions are executed. A serial schedule runs transactions one after another. A non-serial schedule interleaves their operations. A schedule is considered serializable if the result matches some serial execution. The types of serializable schedules. We categorize schedules into conflict serializable schedules, which tested using precedence graph. And second is view serializable schedules, which based on matching reads and write. And third is view serializable is more general than conflict serializability. Conflict serializable schedule. A schedule is conflict serializable if we can convert it into a serial schedule by swapping non-conflicting operations. Conflict occur when two different transactions access the same data from at least one of the operations is a write. And the second is view serializable schedule. A schedule is view serializable if it is view equivalent to a serial schedule. This means the initial read, intermediate reads, and final write must match the serial schedule. Recoverability ensures that if one transaction reads data produced by another transaction. It commits only after the producer transaction has committed. This prevents cascading rollbacks and inconsistencies. Types of recoverable schedules. There are three types of recoverable schedules. First is recoverable, which dependent transactions commits in order. And second is cascadeless, which transactions never read uncommitted data. And third is strict, no reads or writes allowed on item modified by uncommitted transaction. This is the safest form. Recovery from transaction failures. Failures may occur due to system crash, power outage, program bugs, or disk errors. The objective of recovery is to restore the database to the most recent consistent state. And DBMS uses logs, checkpoints, and undo redo mechanism to recover. Next is log based recovery. A log records every action made by a transaction using before and after values. This helps DBMS identify what needs to be undone and redone after a crash. Then types of logging. There are three types of log based recovery are used. First is undo logging. Undo logging stores old values. Redo logging stores new values. Undo and redo logging store both and is used in most modern systems. Next is checkpoints. A checkpoint saves the current state of the database into stable storage, and during recovery DBMS only needs to scan logs from the last checkpoints, and which significantly reduces recovery time. Next is deadlock handling. A deadlock occurs when two or more transactions wait for each other indefinitely, and the system manages deadlocks using prevention techniques such as wait die or warn wait. Avoidance techniques like bankers' algorithms or detection through wait for graphs followed by recovery. Next is concurrency control. Concurrency control ensures that simultaneous transactions do not interfere with each other. It aims to preserve serializability, avoid anomalies, and maintain isolation. Locking is a core concurrency control mechanism. We use shared logs for reading and exclusive logs for writing. Logs allow control access to prevent conflicts. Log compatibility. This slide explains which logs can exist, and shared logs allow multiple readers but not writers, and whereas exclusive logs block all other accesses. Next is log based protocols. There are three major log based protocols. First is binary logging, simple but limited, and second has the two-phase locking, which is also called 2PL, and ensures serializability through the growing and shrinking phases. Third is strict 2PL and holds locks until commit and preventing cascading rollbacks. Time is stamp and based protocols. Here, each transaction is assigned a unique timestamps, and data items track read and write timestamps. Operations are allowed only if they follow timestamp order. This ensures serializability without locks and avoid deadlocks. Validation based protocol. This optimistic protocol assumes conflicts are rare. Transactions go through read, validate, and write phases. Only at commit time does DBMS check for conflicts. Multiple granularity. Multiple granularity allows logging at different hierarchy levels like database, table, page, and record. It uses intention logs such as IS and IX to allow efficient hierarchical logging. Multiple granularity features. The advantage is higher concurrency with reduced log contention, and a transaction can log only what it needs while allowing others to work on different parts. Multi-version schemes. Multi-version concurrency controls stores multiple versions of a data item. Readers can access older committed versions while writers update the current one. This allows non-blocking reads and avoids many conflicts. Recovery with current transaction. When multiple transactions run concurrently, recovery becomes complex. DBMS combines logs, checkpoints, strict PL, and MVCC to ensure correct rollback and redo operations. Introduction to distributed database. A distributed database stores data across multiple locations but appears as a single logical database to users. It provides reliability, scalability, and transparency. Types of distributed database bases. Distributed databases may be homogeneous or heterogeneous. Transparency features hide location, replication, and concurrency complexities from the user. In data mining extracts useful patterns from large datasets. It supports prediction, classification, clustering, and pattern analysis. Next is data warehouse. A data warehouse is a centralized repository for historical data, and it supports analysis, reporting, and business intelligence, not transactional processing. Next is object technology and DBMS. Object technology integrates object-oriented concepts with DBMS, enabling the storage of complex data like multimedia and spatial data. OB, uh, OB, DBMS, object-oriented DBMS, and DBMS, relational DBMS. The difference is this slide compares object-oriented DBMS with traditional DBMS in terms of data models, complexity, and application areas. Temporal. Next is temporal database. A temporal database stores time dependent data with a valid time and transaction time. It is used for historical queries and tracking changes over time. Detective databases. Detective databases store facts and rules. They support inference using logical reasoning and are used in expert system and decision systems. Multimedia databases. These databases manage image, audio, video, and graphics. They require spatial indexing or and storage techniques. Web and mobile database. This database provides lightweight, secure, and synchronized access for mobile and web applications. Thank you.